Hello class. So in last two videos, we discussed about chapter 5 and 6, class 1, 2, and we've learned how to calculate the present value and future value of the four types of cash flows, including lump sum, ordinary annuity, annuity due, and non-even cash flow. Also, we've learned how to calculate the present value of perpetuity, which is payment divided by I. For all the other types, we can always use our financial calculator and use the TVM worksheet or cash flow function to work on these questions. In today's video, we're going to discuss about Chapter 5, Class 6, Chapter 5 and 6, Class 3. Okay, in this video, we're going to discuss how we can calculate future value and present value when the interest rates are not yearly rate anymore. What if we have daily rate, monthly rate, quarterly rate, or semi-annual rate? Okay, how we can convert these rates into the rates that we can use in the formulas or financial calculators. Okay, so we will introduce some new terminologies about how we call different types of interest rates. So we would learn nominal rates, I-N-O-M, periodic rate, and effective annual rate or equivalent annual rate. Okay, and we're gonna calculate these three rates for different interest rates under different compounding periods. Okay, so it could be semi-annual or at more frequency. Okay, and we're gonna learn formulas of how we calculate periodic rate if we know annual rate. Okay, and how we can calculate future value, present value of a lump sum if we have interest rates under multiple compounding periods per year, and how we can calculate effective annual rate or equivalent annual rate from nominal rate. Okay, you might think these formulas look a little bit complicated right now, but after we finish this class, you can come back on this first summary page to be so you could be clearer at that time. Okay. Okay. Okay, so let's start by looking at the first concept here, nominal rate. Okay, we can use I-N-O-M to stand for nominal rate. It is also called annualized percentage rate, or APR, or quoted rate, or stated rate. Okay, so from its name, quoted rate, stated rate, you could tell, or nominal rate, you could tell it is actually the rate that financial institutions usually quote in the beginning, telling you how much the interest rates are. Okay, so this nominal rate is stated in contracts. It is the rate that banks or other lenders tell you they're charging on loans. Same nominal rate can have different compounding periods, and periods must be given together when you are told the nominal rate. Okay, for example, the bank can say that they can lend you this money at 8% interest rate quarterly or 8% monthly. Okay, or if we look at this advertisement here, we can see this is 0% intro APR for 6 months. And after intro period, the APR or quoted rate will be 12.99%. Okay. Okay, so if you see NOM, nominal rates, APR, they both stand for quoted rate. Okay. And for these rates, again, they could be annual compounding, meaning the interest rates are compounded once a year. It could also be semi-annual compounding, meaning the interest rates are compounded twice a year. And they could be monthly, quarterly compounding, okay, depending on the conditions. But once we receive the nominal rate and compounding periods, is this the rate we're going to use in our calculations? Not really. Okay, we have to convert this nominal rate into periodic rate in order to calculate the interest rates. Okay, the periodic interest rate is the interest rate charged on a loan or realized on an investment over a specific period of time. Okay, so especially when our payments occur more than once a year, if you have compounding periods that's not annual compounding but compounded at a higher frequency, you must make two conversions. First, you need to convert the stated rate or nominal rate or quoted rate or APR into periodic rate, depending on what the compounding periods are. Okay, if it's compounded semi-annually, you have the periodic rate will be semi-annual rate. If it's monthly compounding, the periodic rate will be monthly rate. Conversion 2, you need to convert the number of years into number of periods. For example, number of months, number of quarters, depending on the compounding periods. Okay, so in order to do the first conversion, in order to get the periodic interest rate, we need to use the annual nominal interest rate divided by the number of compounding periods. Okay, so I, interest rate, PER, periodic rate. Okay, we use IPER to stand for periodic rate. Could be calculated by using stated annual rate or nominal rate, INOM, divided by M. M means number of compounding periods per year. Okay, so if it's quarterly compounding, then M is 4. We use nominal rate divided by 4 to get the periodic rate or quarterly rate. If it's monthly compounding, then we use nominal rate divided by 12. M is 12 here. So we have periodic rate IPER as the monthly rate. If it's daily compounding, we use nominal rate divided by 365. M is 365 here. So we have periodic rate or daily rate. Okay, after we figure out the periodic rate, we also need to calculate number of periods. We need to use number of years multiplied by periods per year. So we use N, number of years that we've learned in the last 2 videos, multiplied by M, periods per year. Okay, for example, if it's 3 years, semi-annual compounding, then we use 3 years multiplied by 2 because we have 2 periods per year. If it's quarterly compounding, then we use 3 years multiplied by 4. So we have 12 periods. Okay, if it's 3 years, if it's monthly compounding of 3 years, then we use 3 multiplied by 12. So we have 36 as our total month or total periods. Okay, let's look at an example here. What if we want to know the future value of a lump sum under various compounding periods? Assume that we deposit 100 in an account that pays 5% stated interest rate and leave it there for 10 years. What is the future value on the semi-annual compounding? Okay, this is very similar to what we learned in the first class about future value of a lump sum, but here we have semi-annual compounding, which means twice a year for compounding, not once a year anymore. Okay, and also here, what we know is the stated rate, or APR, or quoted rate, or nominal rate. Okay, so we need to convert this 5% into semi-annual rate, the periodic rate. We also need to calculate number of periods, okay, by using number of years multiplied by compounding periods per year. Okay, and then we can use our present value multiplied by 1 plus periodic rate to the power of total periods and multiply by M. Okay, and this periodic rate could be calculated by using nominal rate divided by number of compounding periods per year. Okay, here we know present value is 100. Nominal rate is 5%. APR. And number of years is 10. M here is semi-annual compounding, so M is 2. And we make two changes here. First, we use periodic rate instead of the regular annual rate. Okay, IPR equals nominal rate divided by number of compounding periods per year. So it's this 5% stated rate divided by 2 because we have 2 compounding periods per year. Okay, twice a year. So our periodic rate is 2.5% here. Okay, this is the half-year rate. This is the semi-annual rate. Conversion number 2, we use this number of years, 10 years, multiplied by number of compounding periods per year, which is 2, okay, and multiplied by M. So our total number of periods becomes 20. We have 20 periods here, 20 half years. Okay, so if we want to use the formula, we can use the present value 100 multiplied by 1 plus periodic rate 2.5% to the power of 20. So our future value of this 100 after 10 years or after 20 periods, 20 half years here, is 163.86. Okay, and this timeline shows us exactly why we need to use the periodic rate and the total number of periods, because this initial 100 would be compounded for 20 times, okay, at semi-annual frequency. Another way to solve this question is to use our financial calculator, because here we still have N as but here the N on the financial calculator becomes number of periods. Okay, so we need to input 20 instead of 10 years. We need to input 20 half years as our N. For interest rate, here we need to input a periodic rate, which is 2.5 I. And for present value, we need to input as 100 or negative 100. Either is fine. Let me do negative 100 PV. Payment is 0 and compute for FV. Okay, we have 163.86 here. Okay, what if the interest rates are compounded at a higher frequency, such as quarterly, monthly, or daily? Okay, with quarterly compounding, our M, compounding periods per year, becomes 4. So our total number of periods would become 40. Okay, 40 would be N at quarterly compounding. And our periodic rate would be 5% nominal rates divided by 4, which is 1.25 as our I. If we have PV and payments the same, compute for FV, we would even have a higher number, 164.36, because now we are compounding at a higher frequency. So this potentially gives us higher interest rates, or excuse me, higher interests. So the total money we're getting after 10 years are higher if the principal is compounded at a higher frequency. If we compound at monthly frequency, then we have 10 years multiplied by 12, 12 as M, as our N. Okay, and our monthly rate would be the stated rate 5% divided by 12. Input this as I, compute for future value. We will have even higher number, 164.7. If we have daily compounding, then we have 10 years multiplied by 365, which is 3,650 periods as our N, and our daily rate is 5 divided by 360, so we have 0.0139% as our daily rate. And then compute for future value, we would have, let me try again, 5 divided by 365. Okay, it should be 0.0137 as I, and compute for future value, we should have 164.87 as our final money we receive after 10 years. Okay, so the number keeps going up. When we compound at a higher frequency, we could get a higher interest and principal after 10 years. Okay, so this is how you can solve for such question. Future value of a lump sum using formula and financial calculator. Okay, you just need to change your interest rate into the periodic rate, okay, by using nominal rate divided by M. Also, you need to change number of years into number of periods. Okay, I and N are changed here. All the others are the same as the annual compounding. Okay, so let's look at a question here. Will the future value of a lump sum be larger or smaller if compounded more often, holding the stated I% in the interest rate constant? Okay, so if we have the stated rate or nominal rate constant, if the compounding periods per year is more often, the future value of a lump sum should be larger, okay, as we indicated in the previous example. When there's a higher frequency of compounding, there's more interest accumulated, so the future value will be higher. Okay, what if we are looking for the present value instead of the future value of a lump sum on the various compounding periods? Okay, if we still have $100, but this time it's due after 10 years, we know we will have $100 after 10 years, and the stated rate is 5%, still semi-annual compounding. What is the present value? Okay, so again, the present value of a lump sum formula needs to be changed in two ways. The interest rate should be periodic rate instead of the yearly rate. The compounding periods per year should be the number of periods, okay, should be used here instead of number of years. So we use n number of years multiplied by m compounding periods per year to get the total periods here. Okay, so here we have future value of 100, nominal rate as 5%, n as 10, m as 2 still. All the inputs are very similar. So our present value here would be this $100 divided by 1 plus the nominal rate 5% divided by 2 compounding periods per year. So the periodic rate becomes 2.5%. To the power of compounding periods per year is 2. We multiply it by number of years 10. So we have 20 periods, 20 half years. Okay, so the total present value should be 61.03. Alternatively, we can use the financial calculator, but this time we have our future value as 100. And for n, we need to input number of half years or number of periods, so it's 20. 2 multiplied by 10 here as n. Interest rate, still it is periodic rate or semi-annual rate, 2.5 as I, and we get it by using 5 divided by 2. Okay, still payment 0, compute for PV, we have 61.03 as our present value. We can also input negative 100 FV, so our present value would be positive. Okay, what if we increase the number of compounding periods from 2 to 12? The present value would decline to 60.72 if it's monthly compounding instead of semi-annual compounding. Okay, if we're compounding daily instead of semi-annual, the present value would fall into an even smaller amount. Okay, when we discount more frequently, the present value would become smaller. Okay, so that's how we get our quoted rate from the contracts, and then we convert it into nominal rates and use the number of periods and periodic rate to calculate present value or future value of a lump sum. Another concept we want to introduce here is effective annual rate, EFF, or we can call it equivalent annual rate, EAR. It is the rate that would produce the same future value under annual compounding as would more frequent compounding at a given nominal rate. Okay, so in the contracts, we're given a nominal rate at a certain compounding periods per year. We can convert this nominal rate into this effective annual rate or equivalent annual rate to see how much percentage, what is the rate that's equivalent to this nominal rate if we compound once a year instead of multiple times a year. For example, if we know that we have a investment that gives us 10% interest rate at semi-annual compounding. If we're looking for the effective annual rate, we're looking for the rates at annual compounding, which is equivalent to 10% semi-annual compounding. Okay, so 1 plus effective annual rate to the power of 1 would be equal to 1 plus nominal rate divided by m to the power of m. Okay, because these two conditions are the same, so whenever you multiply by 1 plus effective annual rate to the power of 1 is equivalent to multiplying 1 plus nominal rate divided by m to the power of m. That's why effective annual rate becomes 1 minus nominal rate divided by m to the power of m minus 1. In this example, we have nominal rate as 10% and m as 2. So we just need to use 1 plus 10% divided by 2 to the power of 2 minus 1. So we can get the effective annual rate, which should be 10.25. All right, I just made some edits to the document here so you can see that when we plug the numbers into this formula, the effective annual rate becomes 1 plus 10% divided by 2 to the power of 2. Okay, minus 1. So we have 10.25% as our effective annual rate. Besides using this formula, another way to solve for effective annual rate is using our interest conversion worksheet on financial calculator. Okay, we know the nominal rates, we know M, we want to know effective annual rates. So we can go use our financial calculator here, press second interest conversion, okay, ICONV, which is the same button as number 2. Okay, we can see that NOM appears on the screen. We can either compute it or enter it as the instruction says. Here we know nominal rate is 10%, so input 10, enter as nominal rate. Okay, triangle appears, meaning it's input successfully. Down button. We see EFF. This is what we're going to compute later. So let's press down button for a second time. And we see C/Y, meaning compounding periods per year. Okay, here it's semi-annual compounding, so we input 2. Okay, this is our M. 2, enter. So it's semi-annual compounding. And we press up button, we come back to effective annual rates and press compute. Okay, so the calculator tells you that under semi-annual compounding, the effective annual rate is 10.25. Okay, if you want to clear all the inputs, you can press second clear work. So all the inputs here are cleared except for the C/Y. Okay, and this number 10.25 means that 10.25% at annual compounding is equivalent to 10% semi-annual compounding. These two bring you the same interest rates. Excuse me, same interests. Okay, question. If a loan or an investment uses annual compounding, m equals 1, its nominal rate should be equal to its effective rate. Okay, when m is 1, our effective annual rate becomes 1 plus nominal rate divided by 1 to the power of 1 minus 1. So it is equivalent to nominal rate. If compounding periods occur more than once a year, the effective annual rate is actually higher than nominal rate. Okay, the rate itself should be higher because we only compound for once. It's equivalent to using nominal rates, which is a smaller number, but it's at a more frequent compounding frequency. So these two would bring you the same interests. Why is it important to consider effective rates of return? We get periodic rate, we get nominal rate from the contracts, and then we calculate periodic rate in order to do real calculations. And we get effective annual rate in order to do comparisons. Okay, we can compare investments with same nominal rate but different compounding intervals. You must look at their effective annual returns, EFF, or equivalent annual return, EAR. Okay, they will have different effective rates. Okay, for example, if you have different conditions here, if Bank A says they can offer you nominal rate 10% at annual compounding, another bank is telling you they are offering you 10% at semi-annual compounding. Okay, and we also have Bank C, Bank D, Bank E giving you 10% nominal rate at quarterly, monthly, or daily compounding. How are you going to choose? How are you going to compare them? One way is to convert all these conditions into effective annual rate or equivalent annual rate, EAR, at using our formula or calculator. Okay, so the effective annual rate is 10% for the annual case, 10.25% for the semi-annual case, 10.38% for quarterly case, 10.47% for monthly case, 10.52% for daily case. So you know probably the daily frequency is the best. Okay, it gives you the highest EAR. You can compare all these effective annual rates because they are at the same frequency. Okay, sometimes you get different numbers such as 8% semi-annual, 6% quarterly. It's hard to compare them. So you can just convert the numbers into effective annual rates so they're at the same frequency of compounding. Then you can compare the actual numbers. Okay, the higher the number, the higher the effective annual rate here. We know that it's a higher return that will give us. When is each rate used? Again, for nominal rate, they're written into contracts quoted by banks and brokers. Periodic rate, they're used in calculations and show on timelines. If M is 1, the nominal rate is the same as the periodic rate and same as the EAR. All the three rates will be 1 if it's just annual compounding. Okay, but EAR or EFF will be different if it's not annual compounding and it's used to compare returns on investments with different payments per year. It could also be used in calculations when annuity payments do not match compounding periods. Okay, all of these we will discuss in the future. Periodic rate. Okay, I think we have some repeated words here. Let me add it. Okay, let me pause the video and edit it. Okay, let's look at an example here. What is the future value of annuity under multiple compounding periods? What is the future value of a 3-year 100 ordinary annuity if the quoted interest rate is 10% compounded semi-annually? All right, for this annuity, if we draw it on the timeline, we can see that we have 300s, but this time, because it's compounded semi-annually, so we need to draw 6 time periods, okay, 6 half years, because they could be compounded semi-annually. And for each half year, the rate should be 10 divided by 2, 5%. Okay, and if we want the future value, we can use, if we want to use the method 1 formula, we can compound the first 100 at time 2 to time 6. Okay, by using 100 multiplied by 1 plus 10 divided by 2, 5%, to the power 4, because we compound for 4 half years. Okay, so we got 121.55 as the future value of the first 100. For the second 100, we multiply by 1 plus 5% square. Okay, there are 2 half years. We are compounding it from time 4 to time 6. And we have 110.25 as our future value of the second 100. Okay, so after we compound the first and second 100, the last 100 is already at time 6. So we don't have to compound it anymore. We just add these 3 numbers up. We have the total future value as 331.8. Okay, that's how we treat this annuity as 3 lump sum and compound them to get their future value and add them up to get the future value of a annuity here. Alternatively, okay, because we know that all these 300s occur at the end of each year for 3 years, whereas the interest rates are compounded semi-annually. So how about we just convert this nominal rate at semi-annual compounding into effective annual rate, which is compounded annually. Okay, then we can make this question similar to what we have done before to solve for the future value of this 3-year 100 ordinary annuity at equivalent annual rate, compounded annually. Okay, and I also recommend this second method. Okay, we can first get the effective annual rate by using the formula or calculator. If we use the formula, it's going to be 1 plus nominal rate 10% divided by M2 to the power of M, 2 here. Okay, minus 1. So our effective annual rate is 10.25%. You can also get this number by using the interest conversion worksheet. Again, second ICONV. Nominal rate is 10 here, enter. Down button, effective annual rate. We will calculate it later. Down button, C/Y. Semi-annual compounding. So we input 2, enter. Up button, effective annual rate, compute. So we have 10.25 here. Okay, step 2. Now we know we have this rate 10.25 as I, and this is the annual rate, compounded annually. Okay, we can just treat this as a regular question with annual rates and 300s occurring at the end of the 3 years. Okay, so our n becomes number of years again because interest rates are compounded annually now using this effective annual rate. So we have 3 as n, okay, I as 10.25, present value is 0, payments 100, compute for future value. We have 331.8 as our future value. Okay, if we want to use calculator, step 1, convert this nominal rate of 10% compounded semi-annually into effective annual rate. Step 2, use the effective annual rate with number of years and calculate the future value. Okay, Another example here is the present value of the same annuity. Method 1, you can discount each 100 one by one and add them up. Method 2, still step 1, we get effective annual rate as 10.25%. Okay, then if we want to look for the present value this time, N is still 3 years, I is still 10.25 as the effective annual rate, payment is still 100, future value is 0. Okay, and compute for PV, we see that the present value of this annuity is 247.59. Okay, so that's all for how to calculate periodic rate or effective annual rate from nominal rate, and how to do calculations using periodic rate or effective annual rate. Okay, if you want to do more practice, you can come to the next few pages here. Okay, we have a practice question here of future value of lump sum under multiple compounding periods. Okay, we have the solution using formula and calculator. Okay, please, after you go over the notes, please look at these practice questions without looking at the answers first. Okay, work on these questions on your own. And then you can check your work by looking at the answers here. Okay, we also have example of present value of lump sum under multiple compounding periods. Again, look at the questions first, try to work it out yourself using financial calculator or formula, and check your work. We also have example of how to calculate effective annual rate from APR. Okay, using calculator and formula. Okay, so that's all for this video. In the next video, we're gonna start talking about chapter 5 and 6 class 4. Okay, I'm gonna talk about amortization in the next video. Bye.